Welcome to the 15th lecture for Physics 4C. We use the expressions we derived for relativistic momentum and energy to work out interactions, most of them described as collisions, involving objects moving at relativistic speeds. First, we highlight how involving relativity changes the familiar interactions, using the example of completely inelastic collision. In fact, one of the things we need to get used to is the fact that the total energy is always conserved in special relativity. So, in order to elegantly handle the conservation of total energy and momentum, we introduce the 4 momentum, which, being a 4 vector like the spacetime coordinate, transforms under the Lorentz transformation like spacetime coordinates do. We use this 4 momentum formalism to correctly work out the relativistic inelastic collision and a couple other problems involving collisions. And one more thing, we can also form a 4 vector using the frequency and the wave number of the light wave. So we use the wave number 4 vector to work out the Doppler effect formulas for light. There are more problem-solving examples, including a pion decay example, that I would like to include, but we only have 2 hours for this lecture. Please look for these examples in your homework problems and the lecture notes referred. We start our introduction to quantum mechanics next week.
Okay, so I want to give you an example of collision, and we'll do more examples of collision after we cover quantum mechanics, but I think this is at least something that will get you to think about a little bit more, difference between your intuition that was based on non-relativistic mechanics, and frankly, learning to stop trusting in your non-relativistic intuition. At least once you recognize that you are dealing with a relativistic situation. So let me give you the simplest possible example of collision that I thought was not trivial. So let me give you this. So this is a collision example. And let me do a completely inelastic collision where 2 things stick together, and yeah, so you have let's say flat plane, you have a block of mass m, you have another block of same mass m that's coming in at speed. Let me give you some reasonable speed of 0.9 c. Good? And
sorry, I was like, yeah.
Reasonable relativistic speed. Yeah. I guess I could make it 0.8. Let me make it 0.8. That's probably better. So they collide, and it's an inelastic collision. So after collision, they will stick together. And here's the question. After the collision, how fast do they move off together? Do people remember the answer to this if you were dealing with a non-relativistic physics? What was the answer for this final velocity here? Dimitri?
Is it half if both masses are equal?
Yeah, half, right? Half, so 0.4 c. So this was based on conservation of momentum. And if you remember with the non-relativistic mechanics, if you said it's an inelastic collision, then you'd have said, well, then energy is not conserved. And in the collision, some energy is lost. So let's work out this again using, so this is the non-relativistic answer. Non-relativistic. Let's just try working it out again. This time, using the relativistically correct expressions. Good. So, all right. I guess I will start by copying what we did from the physics 4A. So I'm going to say, well, momentum is definitely conserved. So let me write down conservation of momentum expression. So my initial momentum, that would be gamma based on 0.8 c. I'm going to start subscripting gamma because there's going to be multiple gammas based on different velocities. So gamma and 0.8 c plus 0, it's not moving. So gamma's 1, but v is 0, so it's 0 momentum, is equal to my final momentum, which would be oh, I think I'm going to run into a bit of trouble. Trying to see if I can just do that. I think I'm going to be fine. I don't think I'm going to be fine. Let me just keep going. Gamma times gamma, I'm going to subscript it, some final velocity. And what is your final mass? Yeah, so you might think it's 2m, so let me write that down. That's the part where I think I'm going to get into trouble. I'll explain in a bit. Times your final velocity, so v final. Okay. How many unknowns do you have in this expression? This is known, right? Known. So technically, you might think that you have two unknowns. Do you really have two unknowns? No, you have one unknown because these two are depending on each other. In fact, let me rewrite that expression for v in terms of gamma again. So v in terms of gamma was c times the square root of 1 minus 1 over gamma squared, right? So let me actually rewrite the right-hand side in terms of that so that you are not confused into thinking that there's two unknowns here. There's really only one unknown. And in terms of that one unknown, I can write it this way. So 2m times this c times square root of, so I had the 1 minus 1 over gamma squared. I'm going to absorb this gamma into it. So it's a gamma v final squared minus 1. Good. So, all right, that seems easy enough. So I can solve for the final gamma and get my answer. So let me do that, and then I'll tell you how it's all wrong. I think I'll have enough time to do it twice, once wrong and then once correctly. So to solve for this gamma v final, I have to square both sides to get rid of this square root, right? So let me actually move this over first and then square both sides. So m's cancel out, c's cancel out, so I get gamma 0.8 c times 0.8, the whole thing, whole thing divided by 2 squared is equal to gamma v final squared minus 1. Solving for gamma v final is equal to square root of this whole thing plus 1. So 1 plus, and everything here is actually numerical. Based on v equals 0.8 c, there's a number associated with this. And so that's why I'm just leaving it in that form, because I'm just going to plug in the numbers. So 0.8 times gamma 0.8 c over 2, the whole thing squared. So that's the gamma v final. So let me get a numerical value for this. Let me do it this way. So I need this numerical value first. So that's going to be 1 over square root of 1 minus 0.8 squared. So 1 point that. What is that? Is it 5/3? That's 5/3, right? All right, so let me write this out. Square root of 1 plus 0.8 times 5/3 divided by 2, divide the whole thing squared, and then square root. So 1 point, okay, I actually need that value. All right, so that's gamma V final. Can I copy it? Oh, so that's gamma. So if I know gamma, I can calculate back to V. So let me do that. So that's a square root of 1 minus 1 over that thing squared. All right, so 0.555. So this is the answer we get. The relativistically correct version says V final is 0.555C. So we already get one result that what you would have guessed from your non-relativistic intuition is not correct. You get something that's substantially different. So kind of intuitive answers you had before, they sort of go out the window. Those results looked simple because you were dealing with the low speed approximation. Now that you are dealing with the relativistically correct expression, you'll have to learn to recalculate them because some of the shortcuts you may have memorized won't work anymore. And let me tell you this surprise with the 3 minutes left. This is actually not correct either. If I gave you this to you as a homework problem and you work this out and you plug that into MyOpenMath, it'll keep saying that you got it wrong. And MyOpenMath will actually be right for saying that you got it wrong. It comes down to this. So in working this out, we assume that the total energy is not conserved. Right? We just use conservation of momentum. But so energy, once you account for all forms of energy, is energy always conserved? Yes. Right? So mechanical energy is maybe not always conserved, but once you include all forms of energy, energy is always conserved. And this rest energy includes that all forms of energy. So in special relativity, there's never a situation where total energy is not conserved. When we call something inelastic collision, all we mean is that kinetic energy is not conserved. Whatever energy is not in kinetic energy goes into rest energy. So this is the step I was hesitating because I knew it was going to lead me to wrong answer. This is not correct. That's not correct. Instead, what I have put here is, well, it's some unknown mass m. The mass of the combined thing is not even going to be 2m. That's what you would have guessed non-relativistically, where you're used to saying, well, mechanical energy doesn't always have to be conserved. But I'm saying total energy is always conserved. So you have to, in order to figure this out, you have to write down a second set of equations, which is the statement that, which is this, that the energy is conserved. So if total energy is conserved, then this is what I need to say. The total energy initially, gamma mc squared plus the rest energy of that, mc squared, so gamma 0.8c. That's equal to your final total energy, which would be gamma v final times this unknown mass times c squared. Okay? So you have one more unknown, but you have one more equation to solve that unknown with. So I guess I don't have 30 seconds is probably not enough time to finish it. I kind of don't want to anyway. There's a better way to do this than what I'm doing here. So energy is always conserved in special relativity. In a sense, it's actually conceptually easier. There's a mathematical joke that you will only understand after you've taken upper division linear algebra, which is a linear algebra based on complex vector space, complex linear vector space, is that it's the complex cases that are simpler. Complex meaning complex numbers. it's the more advanced cases where it's conceptually simpler. In low speed approximations, you have to worry about, oh, is my total energy conserved or not? I'm telling you in special relativity, you don't have to worry about it because it's always conserved. This total energy here, this is the total all-inclusive energy that will never be violated. So it's conceptually simpler, but that also means you might have to do more complicated math. And some of that will be helped by what I'm going to introduce on Thursday. This actually simplifies the math that you have to go through quite a bit. So we'll definitely make time to talk about this on Thursday. And I guess, as I said at the beginning of class today, we'll use a little bit of time on next week to wrap up special relativity. Yeah. So, all right, that's probably more on that than I should have spent. And just to make sure we cover all the bases, there is actually a possibility for this to equal 0 without being at the origin. How do you get this interval to be equal to 0?
If you're on the world line of light.
Yeah, if you're on the world line of light, then this is true, which means ct squared minus x squared will be 0. So this, this is the interval I always forget. I think it's called light interval. I think that's what it's called. But this is any interval that can be connected by light traveling between them would be this. Okay. All right, so this is what we covered last time, and this is sort of the geometry that we didn't have time to explore last time. And the reason I'm introducing all of this, this is actually a really useful tool if you are trying to work through those paradoxes, some of which are covered in that note. But let's say you are more practical. You don't care about all this stuff. All you want to do is calculation. You want to figure out what happens in a collision or the reason I'm introducing this tool of 4 vector is because it's useful in a way. Vector was useful for us. So there's a position vector, but that's not the only vector. Force is a vector. Momentum is a vector. What else was a vector? Impulse, but that's kind of momentum. Anything else that was a vector? Velocity was a vector. Acceleration was a vector. Angular momentum. But so you remember how many quantities had a sense of direction? They all were vectors, and you could use whatever mathematical methods you could use space-time with geometry. You could apply that to momentum, right? And what I will tell you is that this 4-vector formalism is similar to that. There are additional 4 vectors that are not just the space-time coordinates. It's another quantity, like dealing with the momentum, that's actually 4-vector. So I want to go over some of those additional 4 vectors. And I think the way to introduce that, so let me introduce this one, energy momentum, by first showing you that I can form an invariant out of this energy and momentum relationship that we have already covered. So let me point it this way. Okay. So I guess I should call this under the heading of energy momentum 4-vector. So we already covered the idea of relativistic energy and momentum. Let me just write down the formulas that were either derived or I just gave it to you. I gave you the momentum. So relativistic momentum was gamma mv. Remember that? Yes. What was the expression for relativistic energy? Relativistic total energy. Yeah, mass energy plus, okay, what was the expression for the mass energy? Okay, so mc squared. And to get from this mass energy to kinetic energy, it's just a simple modification. Yeah, vector of gamma. So this is the expression for relativistic energy. It's surprisingly simple expression. In fact, the kinetic energy is the complicated one because then you have to subtract out mc squared. So what I will do from this point on is that I'm really never going to refer to kinetic energy. I mean, you should know how to switch back and forth, because sometimes a problem will give you the information of kinetic energy instead of total energy. But it's like, if a question gave you information in imperial units, miles per hour, usually the first thing you would do is convert it to SI units, right? So I do the same thing when I'm given information about energy. I first convert it to information in terms of the total energy and then take it from there. So this is what I want to claim and prove to you, that this particular combination of momentum and energy is invariant. And let me try to recall how I wrote it. So this is the combination I remember. E squared minus momentum squared is supposed to be invariant, except if I write it this way, it's a little bit problematic. What's wrong with this expression? Dimensions? Do other people know what Gaussian means by dimensions? Samuel, what do we mean by dimensions? Yeah, it's a kind of vocabulary. Can you look at this and see what's wrong with this? Yeah, the units. And dimension is a synonym for units when we are doing something called the dimensional analysis. Yeah. So yeah, units are wrong. This is in joule squared. So this is in kilogram times unit of energy. Meter squared per second squared. I think that's the correct unit of energy, right? Okay. Squared. And this is in the units of kilogram times meter per second squared. So I'm missing a unit of, I guess, meter per second squared. So actually, depending on the literature you're reading, sometimes you will see this. It's the case where people are working with a unit of c equal to 1. Like if that's the unit you are working with, people will actually write that. But as I promised to you guys at the sometimes early, I won't work in this unit. So what I do instead is I put in whatever factor of c necessary to make the units come out right. So the thing I should do is, I guess, take this divided by c squared. That'll make the units come out right. Yeah. So this is, I guess, a kind of an early warning. If I make a mistake in putting in the correct factors of c, that's just a bad habit from upper division courses slipping through. I'll try not to make that mistake. So what I'm claiming is that this is an invariant quantity. In particular, I am claiming that this is a Lorentz invariant. What do we mean when we say something is Lorentz invariant? I mean, just English-wise, what does invariant mean? And unchanging, right? Not changing. What do you think the adjective Lorentz is referring to? Yeah, under the Lorentz transformation. So under this transformation, I'm claiming this is invariant. Whatever do I mean? I have Lorentz transformation for coordinates, but technically you don't yet have a Lorentz transformation for, energy and momentum. At least I haven't given that to you yet. So one sense in which you can understand this is when we talk about Lorentz transformation, what we are talking about is change of reference frame, comparing something that's at rest with something that's moving at constant velocity. So what I am claiming is that if you write this in any two different reference frames, maybe I'm talking about this 1 kilogram mass, and you could write this in the reference frame where it's at rest, 0, not moving. And if you write this exact same expression in the reference frame where it's moving at half the speed of light, somehow this combination should work out to be the same thing. So let's try that and see if that's what we get. So in the reference frame where this is at rest, what should this combination come out to be? Let me write that on the left because that feels like it's an easy thing to write down. What's the momentum? Yeah, 0. All right. What's the energy? Yeah, so it's gamma's 1 when it's at rest. So it's mc squared. So I have m squared c to the 4th power divided by this. So it's going to be m squared c squared. All right, so the sweeping claim that I'm making is that I can calculate this in any other reference frame, and I'm supposed to get the exact same thing back. I'm supposed to get mc squared back, or mc the whole thing squared. So let me write down here. So this would be in a reference frame. How should I put it? Let's say the mass is moving to right at some speed v. Reference frame where m moving at velocity of beta c x hat. Good? All right. So energy then is gamma mc squared, where this gamma is based on that beta. Right? So let me write that down. So it's a gamma mc squared, the whole thing squared, divided by c squared, minus the expression for momentum is this. V is beta c, so let me write that down. Gamma m beta c squared. I guess that's it. I guess I can factor out some stuff, right? Yes? So let me factor out what factors out. I see a factor of gamma m and c in every one of these. So let me, how should I? Yes, so let me factor out gamma squared, m squared, and I have at least c squared. Then I think actually these factors work out to be c squared, right? C to the fourth divided by c squared, so it's actually the c squared. All right. So with that factored out, what's remaining here is 1. Right, just the 1. Okay. 1 minus, what remains here? 1 minus beta squared. Okay. Anything else you see that cancels out? Yeah, maybe I need red. It's kind of helpful to have some of these formulas just memorized in your head so that you can do the math mentally, because, I mean, I could write it down. What do you see potentially canceling out? Yeah. Gamma with the 1 minus beta squared. Let me write it out so that it's easier to see. Gamma is 1 over square root of 1 minus beta squared. But I'm squaring it. So it just becomes 1 over 1 minus beta squared. So that's gamma squared. Well, these two are the same thing. So they cancel each other out, unless beta is equal to 1. Well, then you end up with m squared c squared, which is what I was claiming that this is always equal to. So this is another Lorentz invariant. Let me write it out in 2 different formats. You can write it in essentially the way I wrote it here. So let me write it out this way, I guess. M is equal to, I'm just solving this for m. You can say m is equal to square root of e squared over c to the 4th minus p squared over c squared. We give a name to this. Let me just give it a grandiose name. It's a bit more pompous than it actually is. This is what's called invariant mass. Or sometimes it's also called rest mass. Does this sound like a quantity that you already know? What's the invariant mass of this 1 kilogram mass?
1 kilogram?
1 kilogram, right? That's what we calculated initially here. Yeah. So what I'm calling invariant mass is what you've known as, this is what you have known as mass your entire career in physics. I guess the only reason I'm pointing this out is there's this archaic phrase called relativistic mass that some older textbooks use. which is going out of style. But in case you see the phrase relativistic mass, the phrase relativistic mass refers to this expression, gamma times m. And I will just briefly say why this expression is falling out of favor. Is that there is no distinction between relativistic mass and relativistic energy. The only difference is factor of c, which if you're in this unit, then it's no difference at all. So that's why this doesn't describe anything that's any different from what you already know as energy. That's why this term is going out of use. When people want to be just extra sure that you are not mistaking what they are calling mass, people say invariant mass. Or you could just say mass, and that means invariant mass. And they should mean invariant mass unless you're talking to someone 80 years old. Old people doing special relativity. Well, old professors. So yeah, so this is another Lorentz invariant quantity. And actually, this is the format you will see this in your textbook. Your textbook will call this mass-energy relationship. So the mass-energy relationship is you could kind of express it for energy. You could say that this is equal to E squared is equal to the rest energy squared. So mc squared plus, and I guess what is kinetic energy? Well, it's not exactly kinetic energy squared, but it is related to kinetic energy squared. Kinetic energy, Pc squared. This is what some people would call mass-energy relationship. And let me just, before we go into break, let me just point out one useful feature of this. The expressions we have been writing down so far, they depended on this mass not being zero. Like if you had a particle that has zero mass, you would run into trouble because there are examples of particles that have zero mass but has non-zero energy. And what you end up having to say is it's 0 times infinity, and I can make the number whatever I want it to be, and which is a bit of a flippant way. I will say this expression is valid even when m is equal to 0. This is correct. So when it's correct when you have m not equal to 0, but it's correct even when m is equal to 0. So for a particle that has no mass, light is actually going to be an example of that. You have energy is given by momentum times c, speed of light. So this is another example of Lorentz invariant. And what that means is that the quantities that are forming this and this can be thought of as quantities here and here. So energy is the time component of energy momentum 4 vector, and momentum is the space component of energy momentum 4 vector. So let me give you the Lorentz transformation for energy and momentum. This is the Lorentz transformation for energy and momentum. I can take this out and replace them with, well, the time component, E over C, the x component, y component, z component of momentum. This corresponds to time. These are your space components. And when you consider this energy and momentum of this object in a reference frame that's moving relative to wherever this is already written, then that's how you would get the new energy and new momentum in that other reference frame that's moving relative to the reference frame where this was described. Well, so let me give you this example. This is actually an example you have seen. And last time I did this, I just told you that I was doing it wrong and never actually corrected it. It's because I was waiting for this to get developed. So let me give you the example again. It's an example of collision, what we would call completely inelastic collision. And I guess we still called it that. So you have some, level plane, mass m, and I have another mass m, which is, the example we used last time was some reasonable speed of 0.8 c that this is moving at. This is at rest. So after collision, what we said was, well, They stick together. It's one big mass that's moving at some speed final. Right? And we looked at this as we are introducing special relativity. Your non-relativistic intuition says that this should be half of this. We got as far as this last time where it's not actually half. But we had to make an assumption about the mass, which I told you then was incorrect. And we never actually worked out the correct mass. So let me recast this problem in terms of conservation of energy momentum 4 vector. So last time we just used conservation of just the 3 momentum vector, as in conservation of the momentum vector that you are already familiar with. Now what I'm saying is, well, it's not just the momentum part that's conserved, it's the entire 4 vector that's conserved. So you could say, all right, then so conservation of 4 momentum, what it's saying is that when you have the 4 momentum component before collision, so total energy before and total momentum before, what this conservation principle is saying is that this ought to equal total energy after and total momentum after. Good? Like principle we are using sounds simple enough? Yeah. And when you write down the exact expressions, let me do that first, because that's where you will see if we have to go through all the math to figure it out, this can get quite complicated. So, so let me write it out. Total energy before. That would be total energy of this mass and this mass. I'm going to use a 1 to label these quantities and 2 to label these quantities, just so that I have something to label my gammas with. So energy conservation says gamma 1 mc squared, total energy of this, plus energy of this, mc squared is equal to the total final energy of this combined mass, which I'm going to call capital M. It's going to have some different mass. It's not 2m. It's something else. So it'll be gamma 2 big MC squared. So that's energy conservation. All right. I think we wrote down momentum conservation correctly last time. Let me write it again. So it's gamma 1 mv1, momentum of this. 0 momentum is equal to total momentum of the whole thing. Gamma 1 big M v, not gamma 1, gamma 2 big M v2. Good. Okay, so we have 2 equations. How many unknowns do we have? Guess we can go through. Do we know gamma 1? Yes, we do. Small m, I mean, these are presumed to be given. V1 is known. Okay. Do we know gamma 2? No. 1. Do we know V2? No. 2. Yeah, if you are counting these as 1 unknown, that's fine. Oh, so we have only 1 unknown. What's the second unknown? Yeah. So we have essentially, so if you count the gamma, then you have 2 unknowns, 2 equations. You ought to be able to do it. But let me tell you this, you will run into some problems. So the biggest problem is, well, actually, there is a way to do it. Let me just tell you what the easy trap that I used to fall into was, so that you will know there's a better way. The easy trap I used to fall into was, I would rewrite gammas in terms of V. So when I see this, my first instinct would say, oh, I need to rewrite this as mv2 over square root of 1 minus v2 squared over c squared. That's my first instinct. And the algebra that results from this first step will usually be complicated because you are squaring stuff, you are square rooting stuff. It ends up being somewhat complicated. And I will tell you, most of the time, when you have to do algebra, it works out a lot better for you if you, instead of writing gamma in terms of V, if you write V in terms of gamma. For one, like if you don't have any intuition for what gamma and V are, you can see that that's actually easier because you have only one thing to rewrite instead of two different things to rewrite. So this is where it's helpful to have this memorized. From this definition of gamma, I happen to have this memorized. V is equal to C times the square root of 1 minus 1 over gamma squared. You've seen me write this down a few times. So that's why I have it memorized after a week or so of doing special relativity, because it's useful enough. So instead of rewriting gamma, I'd rewrite V and write this down. So say that it's a gamma 2 times big M times this, which does involve square root. So square root of 1 minus 1 over gamma squared, but gamma 2 squared. But what you will see is that as you absorb gamma into the square root, it actually simplifies quite a bit. It's a big M times the square root of gamma 2 squared minus 1. And this at least doesn't have fractions. Still at square root, you're still going to need to square stuff, but the algebra that follows from this will be a lot simpler. And after you find the gamma 2, then you can plug it in and find what V final is. Now, let me do a different calculation that actually makes use of what we just went over. So let's say, well, so this wasn't the actual question, but let's say instead of this, we are asked what the mass of the resulting thing is. If you follow this approach, then you really have no choice. Well, I guess you could skip a step, solve it for gamma, plug it in, eliminate it, and then solve for m. I think that might be a way to do it. But let me give you something that's conceptually simpler. So this is what I can tell you that's conceptually simpler. And it often turns out to be algebraically simpler. So this is the conservation of energy and momentum I have. So what it's saying is, well, this is my energy, and this is my momentum. And as long as I'm talking about the total energy and total momentum before or after collision, it's the same thing, right? Now, what I know from this discussion of Lorentz invariant is if I calculate this quantity, E total squared over C squared minus the momentum total squared, if I calculate this quantity, that's going to straight away give me the mass. That'll right away give me, let me write it on the left-hand side. This will right away give me m squared c squared, or in our case, capital M squared c squared. So that's all I have to do now. Yeah?
Is it capital M or 2M? Cause
It's the combined mass of the whole thing.
but it's a rest mass.
Yes.
So rest mass is.
So in the process of collision, what we said in non-relativistic mechanics was that your mechanical energy was lost, right?
Yeah.
What we say now is that in the process of collision, yes, some of the kinetic energy is gone, but that goes into the total energy of the combined mass. So the combined thing is actually heavier than 2m because it's the rest energies plus some additional kinetic energy. That's now in the form of rest energy. Yeah? Yeah. So, yeah, and I can calculate this in any frame, except if I do it here, then I'm just going to get this back, m squared c squared is equal to n squared c squared. I don't want that. Like, I already knew that. I already know capital M is equal to capital M. So what I need to do is I need to compute this in this reference frame. And that'll give me the answer for this right away without having to go through anything else. Let me just go through that and show you. Well, let's go through it and see. So total energy, that's total energy. So that's gamma 1 m, or let me put it this way, gamma 1 plus 1. So gamma 1 plus 1 mc squared divide, or the whole thing squared divided by c squared minus the momentum gamma 1 m1 v1 squared. Yeah. All right. Let me do some factoring. Let me factor out m squared, c squared from both sides. So factoring out m squared, c squared from both sides. Actually, before I do that, let me simplify it a little bit. This c squared, it cancels out one factor of this c squared. So let me distribute this exponent. So square, square, and it remains at 2 because of this. And distributing this, the square, square, square. Good? Yes. All right. Out of this is what I'm going to do. I'm going to factor out m1, not m1. No, just the m. M squared and c squared. Now, it might confuse you a little bit because I don't have any c squared here. As I factor out c squared, I'm just going to put a c squared in the denominator. That way, when I distribute it back in, I still get the same thing. So let me do that. So I get m squared c squared times the rest of the stuff. Gamma 1 plus 1 squared. Gamma 1 plus 1 squared. Minus gamma 1 squared, v1 squared. Gamma 1 squared, v1 squared, and because I'm factoring out c squared that's not there, divided by c squared. Yeah. I can actually simplify this a little bit. That will allow me to bypass plugging in expressions for v, because some things are just going to cancel out. So let me just finish that. So taking this expression, I'm going to expand the gamma 1 plus 1 squared. And then combine that with this. So let me write that out here. So gamma 1 squared plus 2 gamma 1, right? Plus 1, that's gamma 1 plus 1 squared, minus gamma 1 squared, v1 squared over c squared. I see two like terms that both have gamma 1 squared in them. Let me combine the two. So you get first these two terms by themselves, 2 gamma 1 plus 1. And so minus gamma 1 squared times 1 minus v1 squared over c squared. What is this quantity? Yeah, 1 over gamma squared, right? So you get, well, these two cancel out. This is equal to that, so it's 1. I have plus 1, minus 1, so they actually cancel out again. So this, what seems to be complicated expression actually simplifies down to this. This is equal to 2 gamma 1. So that's the answer for the mass. So m squared is equal to small, so that's this m squared is equal to 2 gamma 1, small m squared. And so if I want the answer for just m, answer for just m would be square root of, or square root of 2 gamma times, wait, that doesn't sound right. I messed up something. No, I don't want to deal with the c squared. I feel like that should be greater than 2. What did I mess up?
The symbol in front of the parentheses. Like in front of the parentheses is negative gamma 1 squared. No, at the very bottom.
This one?
the purple one. Yeah.
Oh, I see what you mean. This should have been not minus sign, but plus sign, right? That's what you're saying. Good, thank you. Plus sign. So instead of these two canceling out, sorry about the mistake. So it's 1 plus 1. So this is 2 gamma plus 1, plus 2. 2 gamma plus 2. All right, so that's the correct answer. Everyone follow? Good. Sorry about the mistake. So this is 2 gamma 1 plus 2 m squared. So when you solve this for mass, then it's square root of 2 gamma plus 2 times m. Does this answer make sense? So one of the ways to check your answer, if it makes sense, is to consider its limit. It's what the value of the answer in the simplest case. Here, the simplest would be if gamma was equal to 1 or close enough to 1. So it's a non-relativistic. What do you expect the big M to be in non-relativistic case?
2.
Yeah, 2, right? So if gamma is equal to 1, then that's 4. So square root of that, 2m. Yeah, that's what you would expect. Now, as its speed increases, gamma increases from 1. So this whole number becomes greater than 2. Is that what you should expect? Yeah, as the kinetic energy goes into the rest energy of this mass, and as it becomes greater in proportion, this mass should go up. Okay. So yeah, so this is the calculation that I don't know if it's that much easier. There are other examples where you can simplify what could have been, so it could have been more complicated than this. This is the simpler version that makes use of this expression that's easy to forget, unless you remember it's a Lorentz invariant. Let me do Doppler effect for light first. That's actually easier. With the formalism that I introduced here. How many here remember is the wrong word. When I do physics 4a, I don't cover Doppler effect. So you would have need to read it in the textbook. How many here remember reading about Doppler effect when you did the sound waves? Some of you maybe. Okay, so if you're in my class, sorry, I know for a fact that I don't cover it. If you have read about, if you know anything about Doppler effect, that would be from your own reading. And let me just show you some things about Doppler effect that you may have noticed it at the time. It's quite complicated. When you look at the Doppler effect for sound waves, it's a set of formulas you have to know, and you have to be really careful with these formulas. So Doppler effect. If you have heard of it, and I assume you've read it through all this discussion, I'm skipping it through. What I want to get to is the formula. So they give you this, and you might think, oh, so that's all I have to know. The frequency shift at the observer is given by frequency from the source, given by this ratio of velocities. But if we are just hunting for formulas, what you'll have to be careful is, this is the specific situation with source moving. The next paragraph. There's also a case where the observer, what is it? I may not have read this. Who's moving, source or the observer? So here the source is moving, right? So that figure I think goes with something else. Okay, here. Stationary source, moving observer, that's the formula that they derived here. And there's an entirely separate formula when you have stationary observer and the source is the one that's doing the moving. So when you are looking up formulas for Doppler shift, you have to get both. This for when the source is moving, when the observer is moving. So here this V is the velocity of the observer. And here where the source is moving, here the velocity is the velocity of the source. And you get two different formulas for that. Why is that? Why do we care with the Doppler shift for light? Sorry, not light, sound. That you care, does it make a distinction if it's the source moving or object moving or observer moving? Like physically, is there a difference between, so here I can observe a Doppler effect in two different ways. I could have a speaker that's stationary, and I could be moving, and the sound I hear will change in pitch. Or the speaker can be moving, and then sound that I guess all of you hear will change pitch. Are those two really physically distinct? That it should result in two different formulas. Let me cast the question in a different way. Is there a special reference frame for sound? Yes, there is. And what is the special reference frame?
The medium.
Reference frame of the medium. It's the reference frame where there's no wind, where the air is at rest. So that's what they mean. When they say source is moving, they're saying source is moving relative to air. When they say observer is moving, they're saying observer is moving relative to air. So that's the reason for all this complexity. When you do Doppler effect in non-relativistic mechanics, that's kind of why I skip it. It seems way too complicated. You can read about it. I won't use class time. Now, we are in special relativity. In special relativity, is there a distinction between observer moving or the source moving? Yeah, now in special relativity, there is no special reference frame. So special relativity should turn out to be simpler, because when I have this laser beam, I guess it's bouncing off that and they're coming towards me. And when I say I'm moving towards it, or the beam, the door is moving towards me, either way, it should result in the same effect. Numerically the same effect. So I want to show you a really quick derivation for Doppler shift effect. It kind of relies on a very special knowledge that I have that you guys don't yet because I haven't told you yet. But it's a very simple knowledge that I can just tell you right now. It's the fact that what's called wave number forms a 4-vector. So let me remind you of this. This is a mathematical expression for plane wave. This is what plane wave looks like. Plane wave. So you can describe this f as a function of position and time. You have amplitude times cosine of kx minus omega t. You all remember seeing this? Yes? Good. Now, so this was in 1D, right? 1 dimensions. I have only one space coordinate. Let's say I don't want to restrict myself in to 1D anymore. I want to instead say, I want to describe plane wave in 3 dimensions. It's still a plane wave. It's still going in one direction, but I want that direction to be arbitrary. Then this is the modification I need to make. This x needs to be a vector quantity so that it can be pointing in x, y, or z direction. So this x is vector. And what that means is this wave number here, it's actually a vector quantity. And this product is the dot product. Good? Like this modification makes a sense. Like you might not have known it, but once I tell you that's what it is, it kind of makes sense. Question?
How can you take the cosine of a vector?
I'm not taking cosine of a vector. This dot product is a scalar.
Okay.
Yeah, that's why it's a dot product. Yeah. Yeah. So what k does, this wave number does, is it when you have a displacement, you just look at the displacement along k. So this wave number is actually it's a dot product, and k is a vector quantity. And let me tell you this. This is a Lorentz 4-vector. This particular combination. I hope this is actually quite suggestive. I hope the way this is written is suggestive. I have position and time here, which are components of 4-vector. it's being combined with some other stuff. And I'm kind of hoping this whole thing is a Lorentz invariant. So this thing that it's multiplying to, that's going to be itself a 4-vector. So this is the wave number 4-vector. Wave number 4-vector. Or 4-wave number, if you are naming it the way I named the 4 momentum. Then it should be something like this. The frequency is the time component, somehow. Frequency is in the time component. And the wave number is the spatial component, somehow. Now, I need to fix the unit. So this is correct in the world where your speed, speed of light c is 1. So let me look at the unit. The way the units work out here. So k, anybody here remember unit of wave number? How do you remember unit of wave number?
1 over wavelength.
Yeah, so you remember the definition of wave number. Definition of wave number is 2 pi over wavelength. The important part is over the wavelength. So wave number here has unit of 1 over meter. What's the unit of angular frequency? Not second, but
1 over second.
yeah, 1 over second, or radians per second, but radian is the real unit. So this is 1 over second. All right, so I need to turn this into that. I think I can do that by multiplying this with c. Then I'll have correct unit for both, the units that will match. Yeah? So this is a 4-vector. What that means is this thing that expresses property of a wave, it transforms under Lorentz transformation, like coordinates do. So let's say I have a stationary source. Let's say this is glowing. I have a stationary source, and as it glows, if I describe it, let's say, along this axis, x-axis, if I describe the wave along this axis, then these would be the frequency and the wave number I measure. Now, to get the Doppler effect, what I can do is, let's take the same wave, and let's try to describe it in the reference frame that's moving in the plus x direction. And let's see what we get. Yeah? So then let me skip the y and z component and say that we are only describing the x component of the wave number, just to make things easier for us. So I have wave frequency and wave number in the lab reference frame where the source is stationary, and the primed coordinate that I want to describe is the one that's moving to the right at speed v. So this would be gamma minus gamma beta minus gamma beta gamma. Yep. All right, let's write it out and see. So I do the matrix product. People here remember how to do matrix product? Yes? Okay, so let me erase this and do the product here. So then my first component is gamma omega minus gamma beta ckx. Gamma beta ckx. And I guess that's actually all I need, but let me do the second one just so I have it. Second one is minus gamma beta, or let me do this first. Gamma ckx minus gamma beta omega. Minus gamma beta omega. Good? So this is supposed to be the new frequency. Let me simplify it so that we can get some kind of an expression that we can actually compare to these. They will end up looking somewhat similar to these two expressions. So, well, let me write it out. Omega prime is equal to I guess I can factor out gamma. Gamma omega minus beta c kx. I think I have kx that I don't really want. I want to rewrite it in terms of something else. If the wave is only traveling in x direction, can I rewrite kx in terms of omega? How are they related? Or do you guys remember this? C is equal to omega over k. Coming from speed of light is equal to frequency times wavelength. Seems familiar? I think that was actually on your exam question. Right? All right, so I can solve this for k. Can solve this for k. So k is equal to omega over c. Okay? So this k, let me substitute that in. That's omega over c. Oh, that's good. C's cancel out. So I have this expression, which doesn't look all that simple. Gamma times, so now I can factor out omega. Let me factor out actually omega to the front. So I have omega times gamma times 1 minus beta. 1 minus beta. And when you're just looking at that won't look all that simple. In particular, when you try to compare this to that, like it doesn't look like anything. So let me do this. I can actually rewrite gamma. So in terms of beta, if I do that, then it's this. Divided by square root of 1 minus beta squared, right? Let me do one more simplification. I can actually factor 1 minus beta squared. I don't do that often, but this is a valid algebra I can do. 1 minus beta squared is equal to 1 minus beta times 1 plus beta. Right? That's correct factorization of that expression. So let me do that. I don't do this often because often it doesn't really give you anything useful. But this is an exception. So when I do that, I get omega times 1 minus beta. Let me rewrite it in a strange way. Square root of 1 minus beta squared. That's still fine, right? I haven't done anything wrong yet. Okay, divided by square root of this factorization, 1 minus beta times 1 plus beta. So some things actually cancel out with proper simplification. This factor of 1 minus beta cancels out with that. So you get this Doppler shift formula. So for an observer that's moving away from source, you get omega prime is equal to omega times square root of 1 minus beta over 1 plus beta. So how does the frequency change as you move away from the light source? Does your frequency increase or decrease? Decrease, right? Does that make sense? That is, if you are looking at the, if you are looking at the light, so this is green light. If I move away from that, the frequency of this light would decrease. So what would that do to the wavelength? It'll make the wavelength longer. So if it has a green color right now, as you're moving away, will color shift towards the blue end or the red end? Red end, yeah. So this is called red shift. That's the kind of shift you get when you're moving away from a source. How would this change if you're instead of moving towards the source? Or source is moving towards you? It'll be blue shifted. And the only way this formula will change is you essentially replace beta with minus beta. So it'll be square root of 1 plus beta over 1 minus beta. Pretty simple correction. And so that's it. And this, I guess this is the sense in which this is kind of related to this. In that here, so you don't see any square roots, right? But you do see this, the difference or addition of the source and the wave velocities, or the object and wave velocities. If you did this hypothetical calculation, you do get this result. This is the geometric mean of the classical Doppler shift, where you have two different numbers calculated. So for, where what I was describing, stationary source, observer moving away. In a case of sound wave, it actually matters that this is stationary. But you can calculate two different ways. For the increasing distance, you could say it is actually stationary source, you are moving away, versus you are stationary, source is moving away. When you do those two different calculations, you get two different expressions. One of them, one of them will be this, and the other one will actually give you this. The other one should give you something that looks like, I don't know, PHYS minus V over V, or something like that. So this is what I mean by geometric mean. Everyone here knows what geometric mean is? Geometric mean, average of A and B, multiply them together, take the square root. So you multiply these two together, take the square root, the result you get is this. I don't know if there's any physical meaning, it just happens to work out that way. So that's a Doppler shift. Once you introduce the idea of 4-vector, it actually becomes a lot easier to derive it, because it's just the Lorentz transformation that you've already seen. And what it is the questions in OpenStax don't really go into the level of difficulty I want it to go into. That's why these additional questions are there. And some of the beginning ones won't be all that hard. But as you go into especially the last few, you will find that they are difficult. As in, if you try to, so questions like this one, if you are just trying to write down E is equal to gamma mc squared, then momentum is equal to gamma mv, and you are trying to work through the algebra after applying conservation of energy and momentum, what you'll find is that it's really easy to get lost in the algebra. So that's why it's important, if you haven't already, for you to look at this note that was posted. That's why I did this. This was my highest priority until it was done, because this contains information that's necessary for you to finish the homework assignment. Your textbook doesn't cover it. I needed to cover it. I mean, I kind of covered it in lecture, but you need to have something that's written that you can refer to. And that's what this is. And some of the things we have definitely mentioned in class, 4 vectors, and that energy and momentum form a 4-vector, and that there's a Lorentz invariant. Like all of this were mentioned in class, but what we didn't have a lot of time going over, and you really need a written material to refer to, is how these apply in the context of problem solving. So look through it. Some of the examples we actually looked at in class, like redshift starlight, it's a version of what we did in class. So skip it if you want, skim it if you want to. But the questions that will become quite similar to the questions you need to do on the homework assignment are the last few. It kind of ramps up to it, so do read it in order. But it's the last few examples. So this one is one where, sorry, I realized it as I was answering someone's question that I didn't draw any figure. That's why you kind of have to read it through it. Draw your own figure. This one describes collision between a stationary target with an energetic target coming and hitting it. This is like 1 or 2 of your homework questions. And the calculation approach you see here will be very different from the one that you might intuitively do starting from this. It's because I'm treating energy and momentum as proper 4 vectors. And the thing that I start out by calculating is I start out by calculating the Lorentz invariant instead of going through this expression. I mean, at some point it comes in. So at this point, I do bring in that energy is expressed as this. But it's not until the very end that it actually comes into a vector. So when you do special relativity calculations, really the number one thing I would say, try to avoid this, is getting bogged down in algebra. If you are finding that you need to do pages of algebra to do a problem, chances are there's a better way. Whatever you're doing, this is what I used to call soft error in physics 4a, as in you are doing something wrong, but not in any identifiable way. You are not making any algebra mistakes. You haven't written down anything that's wrong, except in the sense that you are not getting towards the answer. And when you get stuck in that, this is part of the problem-solving skill that you need to develop. When you get stuck in something like that, you need to recognize, all right, this isn't working. You need an entirely new approach. And what these examples are giving you is that entirely new approach. That algebraically, these are actually very simple. But what they are more complex in is the sort of the mathematical tool that it's using. 16? Okay. The whole thing. Oh, I guess, yeah, I probably should do this as an example. Yeah, so let's do that. So yeah, try your best to follow. But in case you are having difficulty, this is one of the scenarios that are covered in the note. But let me do this as an example because this is a common one, and this is one where this calculation technique that's introduced in the post-it note is very useful in avoiding a bunch of difficult algebra. So this is the situation. You have a collision involving two particles, and one of them is at rest. And there are many different scenarios that can be described in the same picture. That's what you have in your in the post-it note. So let me call it relativistic collision. And I will deal with it in a general sense and then plug in the numbers after so that you can see the general approach we are taking. So we have a particle at rest. And we have another particle of higher mass that's going towards it. And it would be easy if they gave us the velocity, but they don't, right? So it's asking for what is the threshold energy? So this particle that's moving towards the other particle, you could characterize it with some velocity, or you could characterize it with some energy or momentum. If any of these quantities are given, then this problem becomes much easier to do. What's hard here is that they are asking for any one of these quantities. And working that backward is the hard part. If you're trying to go through this algebraically the way you might normally do, that's where the calculational technique that's introduced in the note is introduced. So let me quickly demonstrate that. So what the information that the question is giving is, question of this type is giving is, so you have this collision, and when the collision happens, this is an inelastic collision. So after the collision, you get some kind of a blob of thing that's moving together, some kind of final. And this blob of thing could be something of just a single mass big M, or in this question, this blob of thing would be actually proton, proton, and a pion. But it's asking for the threshold energy. So it's asking for the situation where all those three particles are moving together. They're not moving relative to each other because that's where they would have least amount of kinetic energy, right? Yes? Okay. So in this particular case, it's a blob of mass M, and another mass of pion. Good? Yes? But let me deal with this in a more general sense, and let's say this is just a big mass, big M. Yeah, either way is fine. So, all right, so you look at this, and does it feel like it's a question where we should use conservation of energy and momentum? Right? Okay, everyone has that intuition, that's good. So we start out with the conservation of energy and momentum. So we say sum of total energy before collision is equal to sum of total energy after collision. And we say sum of momentum before is also equal to sum of momentum after. And it's easy enough to write down these expressions. Let me do that. The total energy before collision is the rest energy of this particle, and the rest energy of this, total energy of this particle. So let me call it, I guess it's asking for the threshold energy. So let's give this a symbol, E sub t. So this would, total energy before would be E sub t plus mc squared. Okay. All right. Total energy, so this should be equal to the total energy after, which would be, it's however fast this mass is moving. And this is where it may be tempting to write down gamma big MC squared, right? I guess I can leave it there for now. Let me just leave it there. So let's say you have conservation of energy expression, okay? And you have conservation of momentum expression. So that would be, so this says 0 momentum. So you're just counting momentum of this. So let me just call it threshold momentum. That's equal to momentum after. So here you might be tempted to say gamma big MV. And what can get algebraically very complicated is if you are now trying to, express these in terms of second set of gamma and V, and try to somehow solve them, eliminating these sets of gamma and V. And that's where I'm telling you that's algebraically complicated. It'll take, I don't know if I can do it that way. This is where the idea of Lorentz invariant is helpful. So the idea of Lorentz invariant is that there are certain combination of quantities that in whatever reference frame, it gives you the same thing. So we talked about invariant interval in this class, and we didn't spend as much time with the invariant mass, and that's why I'm calling it invariant mass, even though it's mass, is that there's this expression that is valid. Mass squared, I guess I want to actually put it this way, mc squared is equal to E over c squared minus momentum squared. So the way I would like everyone to eventually think about this is the inner product of the energy momentum 4 vector to itself. So energy divided by c and momentum, that's the energy momentum 4 vector. When you take a dot product with itself, that's what this is. Time component squared minus the spatial component squared. And that is equal to the Lorentz invariant, which turns out to be mass. So that's how I want everyone to think about it. But if that's a little bit too far beyond, that if you feel uncomfortable thinking about it that way, you can think about this as a rewritten version of this energy momentum relationship that says that energy squared is equal to mc squared plus pc squared. This is the energy momentum relationship, right? It's a simple algebra going from here to here. So either way you think about it, it's fine. And either way, what you should notice is that this m here, this is the property of the particle. This is why the idea of invariant mass is important and much more useful than relativistic mass. Because with this mass, you can say, however you find this mass, it's property of the particle, it doesn't change. When a particle of mass m is moving at close to speed of light, it still has mass m. It doesn't have a different mass. Okay? All right, so this is what I'm going to use. I'm going to take this equation, and I'm going to simply compute this quantity here. energy squared minus momentum squared with appropriate vectors of c so that the units come out right. Yeah. All right, so let's do that. So the left-hand side becomes this. This is the left-hand side. So energy squared. So ET plus mc squared minus the momentum squared. That's the left-hand side squared. And the right-hand side squared would be, let me do that in different color. Right-hand side would be this squared minus this squared, gamma big MC squared. Oh, wait. I forgot a vector of c somewhere. Sorry. I'll do that in red. So energy squared minus the momentum squared, gamma mv squared. And let me just put in the correct vectors of c so that I guess I should be putting here. Divided by c squared, divided by c squared. Everything good? Yes. Does everyone recognize the second set of expression as simplifying? So you can factor out a vector of gamma squared. And when you factor out a vector of mc squared, or m squared times c squared, you end up with 1 minus v squared over c squared. So all of this really simplifies to big MC squared. Does everyone recognize that? It's taking longer than I'm expecting to hear an answer. Yes, so let me just do the algebra quickly on the side here so that everyone can see that. Let me factor out gamma squared. So with the gamma squared factored, it's a gamma squared times, in fact, let me do this. I'll factor out gamma squared, m squared, and c squared. So gamma squared, m squared, c squared. So out of here, I only have just one remaining, right? So 1 minus, here I'm factoring out gamma squared, m squared, and I'm factoring out a c squared that doesn't exist. So it has to be v squared over c squared. Yeah? Now, gamma squared is equal to 1 over 1 minus v squared over c squared. So this gamma squared will cancel out this. So you end up with m squared c squared. This is sort of an illustration of why it was unnecessary to describe this as gamma and v. In terms of, you could just said this is the E final and P final. And when you had written E squared minus P squared, you would have seen from this, oh, I'm just going to get invariant mass. Yeah? All right, so that's the right-hand side. Very simple, just the mass here. So left-hand side takes a little bit more work. Let's see what cancels out, how it simplifies, and how we can get to the final answer. So the left-hand side, let me expand this out, and we will work through carefully what that turns out to be. So I have E squared divided by C squared. So ET squared over C squared plus the cross term, 2 times this divided by C squared. So plus 2 ET M, and then C squared divided by C squared cancels out. So this is what I have. And then this thing squared plus M squared, and it's C to the 4th power divided by C squared, so C squared. Yeah? So that's just this expanded out, and then I have minus PT squared. This is where it helps to learn to group group some terms together. This term in particular, I would like to group it with this. Do everyone see why? What is E squared minus momentum squared?
Mass.
Yeah. It's the invariant mass, right? By the way, when I'm saying it out loud, I'm skipping C's, but when I'm writing it down, I'm writing down correct factors of C. So I can combine these two to get mc squared, right? And then plus, I have this still, 2etm, and this mc squared. Well, all right, so I have two of them instead of just one of them. So I have 2 mc squared. So that's the left-hand side. This is the right-hand side. From our starting point, we know these two are equal to each other. So this is equal to that. And now the rest is actually pretty simple algebra, because it's a matter of, well, all these are constant, so it's, move that over and solve for E of t. And, well, I guess while we have done most of the work, so let's just finish it. Let me solve it for E of t. So when you do that, what you get is E of t is equal to this thing minus 2mc squared. So capital MC squared minus 2mc squared divided by 2m. And here, let me just double check that the energy that they want is the total energy. It doesn't say kinetic energy anywhere. Includes the rest energy. So it's just asking for this actual total energy, not the kinetic energy only. Let's plug in the numbers. And I'm going to make the use of the fact that the way our units are specified, I can actually essentially ignore factors of C. Because the way that's how it kind of works out. If you do the calculation carefully, all these factors of C will just serve to cancel out these factors of C in the units themselves. So, no, I forgot a factor of C here somewhere, I think. Where did I forget a factor of C? No. I think it actually works. Yeah. I didn't forget a factor of C, but I'm going to ignore all the factors of C now because that's how my units work. So let me just plug in all those numbers. All from alpha. So, let me do it this way. So this big M, it's mass of the protons plus the pion. So that would be 938 times 2 plus 135. So 938 times 2 plus 135. Plus 135. So that's this. I need to square that. And then subtract 2 times the proton mass, 938 squared. And then divided by twice the proton mass, 2 times 938. And my units are going to come out to be MeV. I get 1218 MeV. Let's plug it in and see what I get. 1218 MeV. It'll be embarrassing if it's wrong. All right, good, it's right. So that's how you do this calculation. And once again, you have a written example in the note that I posted. And this is how you should approach this calculation, not trying to solve for gamma and V algebraically. You should use the Lorentz invariant. Yeah. So this is the setup. Let me call it collider configuration. And in the example, I'm using numbers, but let me just do it algebraically without any numbers. So let's say you have two particles of the same mass that you are making them collide. So two particles of mass m that are coming towards each other, that's colliding. And as they collide, let's say you are creating a single particle of some big mass m. Okay? and you are given the energy of the beam. Let's say the particles in this beam have energy E1. And actually, particle in this beam has the same energy, E1. Good? And the question, so this is the part B of that example 2. The question would be, so let me renumber here, A. What is mass of the single particle mass big M? This one, if you have the right intuition, you might be able to answer really quickly without writing down a bunch of formulas. Like, what should this mass be? No answer. Well, let's write it down. All right. So if you had the intuition to write it down, great. If not, let's just go through the steps. So what principle are we using here? Where do we start?
Conservation.
Yeah, conservation of energy and momentum. So let's just write down the conservation of energy and momentum expression. So energy is conserved. I'm told that I have E1 and E1 here. So energy conservation says that E1 plus E1, or 2 E1s, is equal to, what's the expression for energy after collision? Yeah, just the rest energy of this single particle. Could this particle be moving? There's something that prevents this particle from moving at all.
Conservation of momentum.
Yeah, conservation of momentum. So Gaoja, what tells you that net momentum here, what tells you that net momentum here is equal to 0?
Opposite direction, but equal energy.
Yeah. Equal energy, meaning equal magnitude of momentum, and they are going in the opposite direction, so the momentum should add up to 0. So now here's one useful fact to know. Wait, useful fact? I don't know. Here you can kind of figure out, okay, you have net momentum equal to 0, single particle, its velocity is 0. Right? Okay, none of this is surprising to people. Okay, so energy conservation, so you just have the rest energy mc squared here. And I guess we could write down momentum conservation, but kind of don't need right now. So it's looking for mass. So mass here would simply be 2E1 divided by c squared. That's kind of it. Simple. Right? So this is what I was referring to as the center of momentum reference frame, where your net momentum is 0, and especially if you have a single particle in the reference frame, things are super simple. Because, well, you just add the rest energy and that's it. E equals mc squared. No gammas or nothing to worry about. Okay? So now what I want to have about 20 minutes or so to go through is the more interesting situation where you are no longer in the center of mass frame, but this single particle may be moving. So I think this is one situation where it's kind of more useful for me to give some numbers. So let's say we want to arrange this in such a way. So this is for part B. This is how I want to arrange it. So let's say these energy E1, they were the maximum possible energy in this collider. But what I can do is I can decrease energy of one of the two beams. So instead of E1 and E1, now what we have is, well, E1 still here. And this particle will now be coming with some energy. Let me call it E2 less than E1. And the goal of changing this arrangement is to make it so that the particle that's being produced here, which will have some mass big M, different big M than this, but some mass M. But after being produced, I want this particle to be moving to the right with a speed 0.5 c. Yeah. So this would be the question that someone could ask. Well, I'm sorry, this is the second setup. And the two questions that someone could ask are B, what is value of E2? How much should this beam energy be reduced so that whatever resulting particle is, it's moving to the right? And the other question you could ask is, well, what is the mass of this particle now? Because it's going to be not the same as this. Does everyone see intuitively that this mass is not going to be the same as this? Like intuitively, how would you explain that? Is this mass smaller, greater, smaller? Smaller. Okay, why is it smaller than this?
Some kinetic energy.
Yeah, so it's smaller for two different reasons. One is the obvious one, that E2 is decreasing. So there's smaller amount of energy to start out with. And the second thing is what Gaudio was referring to. In this final system, some of that energy has to go into kinetic energy. So this is just for the rest energy. So it's going to be smaller for two different separate reasons. So, all right, so those are the questions. And the situation seems well specified enough, like you have all the details you should need. So how would you answer that? Let me change the situation a little bit and see if it'll be easier to answer. So this is how I want to change the situation. So in this situation, it's not very easy because, because this particle is moving. You don't know its mass. You don't know how fast it'll be moving, but you don't know its mass. That's, I guess, the big thing. So let me describe, let me give you an alternate reference frame to describe this same exact picture in this alternate reference frame, this particle of mass m that gets produced, it's going to be at rest in this frame S prime. So, well, this one of the particles that's colliding, that's producing it, that'll be coming in with some energy, E1 prime. I don't know what that is yet. Maybe I'll get to it. And this other particle that's coming in of mass m, that's coming in with E2 prime. Now, in this reference frame, frame S prime, do you know how E1 prime and E2 prime are related? How should they be related?
For 4 vector.
You can write 4 vector. I'm looking for a simpler answer. Like there's something about E1 prime and E2 prime you know right from the beginning, from the specification that you are in the center of mass frame or center of momentum frame. Man. They should be equal to each other, right? In this reference frame, you can immediately say that E1 prime is equal to E2 prime. So that net momentum works out to be 0, and you get all that nice stuff before. Yeah? So let me ask you this question. You already know what E1 is. That's a given. Do you have enough information to calculate E1 prime? Or let me put it differently. Do you know what change of reference frame transformation relates this reference frame, frame S, to this reference frame? What's the relative speed between them?
0.5.
Yeah, 0.5c, right? Because you imagine you are looking at this particle moving at 0.5c relative to this frame, then this particle should be at rest. So this is the situation where you have a reference frame with the known boost parameter. You know how fast the frame should be moving. So once you have that, then you have this useful Lorentz transformation of energy and I guess I never wrote that momentum. So energy and momentum form 4 vector, which means they transform under Lorentz transformation like coordinates do. So let me write it down. They transform this way. So let me use black pen. So given the energy and momentum in frame S, the energy and momentum in the primed frame that's moving to the right at some velocity v, it's given by this. E prime is equal to, let me write, E prime divided by C is equal to gamma E divided by C minus beta P, well, X technically. And Px prime is gamma Px minus beta E over C. If you remember Lorentz transformation, this is taking the role of the time coordinate. And this is taking the role of space coordinate. Or in this case, I'm just writing down space coordinate x, because y and z do nothing interesting. Okay? So this is your prescription for if you know the energy and momentum in one reference frame, how you get energy and momentum in the other reference frame. So here, so here, this is the step that I'm going to walk through. So I know the energy, which also means I kind of know the momentum. And because I know these two, I can plug those in to get what the energy E1 prime is in the frame S prime frame. Then in this easy reference frame, I can figure out what E2 prime should be. I can write down the momentum 4 vector for that corresponds to E2 prime. And I can do the reverse Lorentz transformation. And reverse Lorentz transformation is kind of easy. So I guess you could do algebra through this to figure it out. Or you can intuitively figure, well, going from frame S to S prime is a frame moving to the right, right? Well, going from frame S prime to S is frame moving to the left. So wherever you see beta, you replace it with a minus beta. That gives you the reverse transformation that looks like, let me copy it down. E over C is equal to gamma E prime over C plus beta Px prime, and Px is equal to gamma Px prime plus beta E prime over C. So once you figure out E2 prime, write down the energy momentum 4 vector, put it through the reverse transformation to get what E2 is. So that's the easy 3 steps to go through to find out what the energy E2 is. And along the way, you would also find out what M should be. Good. I think I have 10 minutes, and I can do this in 10 minutes if I'm allowed to use something called ultra-relativistic approximation. This is an approximation that is correct with the numbers that are given in that example. And this is the approximation that I'll be using so that I can work through this in the amount of time. Otherwise, the algebra gets a little bit long. So this is the approximation I'll be using. Approximation is that E1 and E2 are both much greater than mass m. As in, the total energy of the particle is much more than the rest energy, maybe 10 times more. That means factor gamma is about 10 or more. And what that does is that makes it essentially so that the velocity of the particle, if I ever need it, is approximately c. And the second part, this is the more important part, I can say, so that's true, and I can say E1 is approximately P1c, because the mass is negligible. Okay. All right, so this is called ultra-relativistic approximation. Ultra-relativistic. And it's quite common in high energy particle physics where velocity of the particle is really very close to c, like 0.999 c or something. Okay. All right, so let me proceed with that approximation. That'll make it easy enough for me to go through this. So let me write down the 4 vector that corresponds to E1. So that for energy momentum 4 vector would be this. So E1, I guess divided by C. And I guess momentum is plus E1 over C also. Right? Okay, so that's the energy momentum 4 vector. And this time I'm going to write down the Lorentz transformation in the matrix form. In the matrix form, it looks like this. Multiplication by gamma, minus gamma beta, minus gamma beta, gamma. Right? So what I get here will be my E1 prime, P1 prime. So let me just work out E1 prime. So the from here, E1 prime, divide by C. So V1 prime divided by C is equal to gamma times that. So gamma, and I guess I should specify so that it doesn't get confused. This gamma is the one associated with the 0.5 C. Right? Yes. So beta is actually, I know the value of the beta. This is 0.5. Good. So let me just keep gamma as is. So gamma sub 0.5, and this is a reminder. I know what the numerical value of this is. I can plug it in to figure out what this is later as soon as I want to. So gamma times E1 over C minus gamma 0.5, and this time I'm just going to plug in beta. So beta would be just 0.5 times E1 over C. So I have E1 over C on both sides. Let's factor it out. E1 over C times, and I have gamma minus gamma beta. Let me just work out what the numerical factor of that is, and just plug that in. That'll be easier. So gamma with a beta of 0.5 would be 1 over square root of 1 minus 0.5 squared. That would be 1.155. So it's 1.155 minus 1.155 times 0.5. So let me just plug in all the numbers so that things are easy for me. I guess I can do this. This times, 1 minus 0.5, which is 0.5. So E1 prime is E1 times, so this is what you end up with. You get E1 prime is equal to 0.577 E1. Good? Then which tells you that, so this means that this is also equal to E2 prime. Good? So let me write down the 4 vector that corresponds to this E2 prime, and then do the reverse Lorentz transformation to get the E2. So now, if you are thinking about this naively, you might think, wouldn't I just get the same E1 back? But the important thing is the direction of momentum is different. And that's going to make all the difference. Because in the reverse transformation, you are not going to get an increase in energy. You are going to get another decrease in energy. So let me write it out here. So this is my momentum 4 vector. I guess, so this is what this is supposed to be is E2 prime divided by C, P2 prime. And using this value to write it out, it's a 0.577 E1. And momentum, it's going to left, divided by C. So it's minus 0.577 E1 over C. This is the E2 prime momentum 4 vector. The reverse transformation, it would be the same gamma and beta, but it'll be gamma times plus gamma beta, because I'm plugging in minus beta in place of beta, plus gamma beta, gamma. So, and the result you get here is going to be E2 over C and P2. Okay? All right, let's figure out what this energy E2 is. Let me use this space here to figure out that E2. So E2 is equal to, so I have, I'm going to say I pre-multiplied through C, or let me not be unnecessarily confusing. Okay, so E2 over C, I'm just writing out this matrix element here. That's gamma times this. So gamma times 0.577 E1 over C plus, but oh, there's minus sign. So it's minus gamma times beta, which is 0.5 times 0.577 E1 over C. So let me just factor out some things. So factor out E1 over C times 0.577, which is in every one of these, times I have gamma times, so it's gamma times 0.5. I think I worked this out before, right? Gamma times 0.5, that was this. So the result you get is you just square this. So the value of E2 from all of this, E2 is, I don't know, 0.55 squared. So so E2 is equal to 1/3 E1. Okay. So that's it. That's and you know, this is not an intuitive answer in any sense of the word. Like if you're looking at this, you wouldn't simply guess, yeah, to make this move to the right at half C, you reduce the energy to 1/3. You wouldn't say that. Like I couldn't guess that. But the steps you work through is this. So you realize that this situation is much easier to analyze in the center of mass frame. So you go to the center of mass frame and then figure out the energy in center of mass frame, or sorry, center of momentum frame. And then using that, using this center of momentum frame for momentum, you can transform it back to the frame S to get the energy in the lab frame that you wanted. Now, if you want the mass, you can figure this out in the center of momentum frame. Because I guess what I'm figuring here, okay, so this must have been 1/√3 E1, right? So in the center of momentum frame, the total energy was 2/√3 E1. That's how much energy there was in this frame. And the center of momentum frame, all this is rest energy. So this mass here must be 2/√3 E1 over C squared. And because this mass is a Lorentz invariant, you can calculate it in whatever reference frame it's convenient for you. It's more convenient for me to do it here, so I do it there.